All right, everyone, welcome back to another hottest seminar in fall 2020, or no, in spring 2022. This week's speaker is Marcelo Fiore from Cambridge, and he'll be telling us about the mathematical and computational meta-theory of second-order algebraic theories.
Okay, thanks a lot, Carlo. Thanks a lot, all the organizers, for the invitation. It's a pleasure to be talking here. It would have been nicer to do it in presence, but never mind. So I want to talk about some joint work with a PhD student of mine, Dima Samos-Banzev, which is quite recent from one point of view, but has a lot of theory that has been developed over the years in the background. So it's essentially about second-order algebraic theories, which I will explain what they are as we go along, mainly with a lot of examples. The mathematical theory of which has been studied for a while, as I have kind of mentioned, but we want to focus here on the computational aspects of the meta-theory for reasoning about them. So that's the focus of the talk. Before that, I would like to to put the research in some kind of context for a few minutes, so that you understand where it is going and which kind of a piece of a puzzle this is. So the general theme is that of what I like to call algebraic type theory. The main research question underlying this development is, what is a type theory? And when I ask the question, and ask it both from the point of view of logic, as we use type theories, but also from the point of view of computer science, where many times the type theories are kind of motivated from sometimes logical foundations, but in fact they may not correspond one-to-one to logical theories. And the question has to be focused from my approach from 2 points of view, a foundational one and also a pragmatical one. So the foundational one is mainly trying to understand what kind of mathematical models are type theories. And from this viewpoint, I take a particular approach, will become clearer as we go with this one example I'm going to look at. The pragmatical point of view is it has to do with the formalization and programming, and it's closely connected to being able to do computations. So from one direction, it should kind of be connected to programming practice or to implementations of type theories, or at least to inform the development of just research. And the working hypothesis that I use throughout is that the type theories are algebraic systems. Now, this is a very broad statement. And so here, algebraic system is taken in from a very wide point of view. It's mainly encompassed by categorical algebra, and so you will see that throughout the talk I will be using a lot of categorical machinery. And most of the time, what I think our kind of task is in this area is to really understand what is the algebraic structure that lies underneath the type theories that are being developed. Okay. This is by no means an easy task and can be quite hard work, but that's the overall idea of the approach. Okay, so I'm going to look at the most trivial example. It's very trivial, but in fact I find it very important to concentrate when actually looking at general theories. For instance, even from the dependent type point of view, it is interesting to see when a dependent type theory boils down to this very simple setting, which is the one of equational logic of universal algebra, as put forward and developed by Birkhoff. Okay, so in that setting, we have types and terms, and they have essentially very basic structure. So the types themselves are typically called sorts because in fact they have no structure whatsoever. While the terms, they have what we now call algebraic structure, which I would say is first order. So what I want to talk about today is one step in conservative extending this system. Okay. The step consists in kind of translating the term structure to the types, so that now the types have a first-order algebraic structure as we know them from universal algebra, and something that is completely and very well understood, while the terms get a new dimension, and this new dimension is second order, by which I will be explicit what I mean in a minute. The system that we get is actually a conservative extension, and the very first part of the talk will be about giving you examples of such systems. So second-order algebraic theories, I put them forward with a couple of PhD students some time ago. I would say they are equational deduction system or rewriting deduction systems for languages with these two kind of features that I talked about before. Type structure, which is of first order algebraic and therefore completely well understood from the point of view of category theory, universal algebra, even functional programming with data type theory. And then the term structure that is second order, and by that I mean two main ingredients. We have variable binding operators and also parametrized metavariables. So these two ingredients, they were introduced as well a long time ago, quantifiers by Frege. And as far as I know, but I'm not absolutely sure, these parametrized metavariables, of which I will give you many examples, were introduced first by Peter Axel in '78. Okay, so the plan of the talk is as follows. So first I want to give you an idea of what you can do with these second-order algebraic theories, and I will do this by example. The example will be of incremental order, so that you see the kind of aspects that I want to get out of these algebraic theories. Then I'm going to look at the mathematical foundations. This is from the categorical mathematical point of view, well understood. But I will try to see how we can look at it from the point of view of computer formalization. And what we will see is that there is quite some tension in trying to port the mathematics to the computer language. And this, in fact, triggers a new mathematical model. And so that, in fact, comes together with the computer implementation. The aspect we are going to focus in order are first, how to implement syntax, both with this binding and metavariables. Next, we'll look at the notion of substitution that comes with each of these features, which are of two kinds, capture avoiding and meta-substitution, as I will introduce. And in doing this, I will mention in passing the semantics that comes with the mathematical modeling, which is, as it should be, completely algebraic. Okay. So I said that these second-order algebraic theories are a conservative extension of universal algebra. So let me start with an example from universal algebra, namely Boolean algebras. So here I'm considering propositional logic then. This code snippet is actually code that you can put in a system that I'm going to give you an idea that we have developed, and I'm going to give you an idea of how you work with, okay, and what you do with it. So we declare a sort, it's zero array, so it has no structure. True and false are constants of this sort. We have binary operations, and or, and unary operation not. Okay. Now, in this theory, as you expect, you write algebraic terms and you put equations between them in the usual form. And what you are interested here is how, from this description, generate abstract syntax for reasoning, well, for talking first about this language and then for reasoning. And reasoning is by means of substitution, as we understand it in universal algebra. Okay. So a system for doing such equational reasoning, it's clearly understood, and what we want to do is to extend it to second order. So the first example of such a system would be first order logic. So first order logic is itself a second order theory of a particular kind. We extend propositional logic with the quantifiers. Here we have for all and exist. Notice that now the notion of arity has been enriched. For all is an operator that gives a proposition, but is parametrized by taking propositions unbinding variables from a universe n of individuals. And the same for existential quantifier. In this setting, now we can write logical formula here in ASCII, but from which we will actually generate formal syntax. And I'm going to go through that as we go along. Say according to some equational theory again, and here are some examples of equational laws that you may want. So for instance, the Morgan law that says that not for all is the same as exists not. Or here some kind of axiomatization of for all. This is for all x p of x holds if and only if for an arbitrary n, p of n holds, and for all x, p of x holds. Okay. And now what we are interested in is, within this formal theory, do equational deduction so that proving well, equivalence of formulas. The question is how we are to do that. And so I'm going to give you an example of the idea behind. So here we have, we want to prove that the exist x f of x implies q is equivalent to for all x, f of x implies q. Okay. Now, already in this formalism, there are things that are implicit and actually give some kind of a nice expressive power to the system. This identity is allowed, provided that when Q is moved within the for all quantifier, there is no capture of bound variables, of free variables, sorry. Okay, and in fact, this is implicit in the formalism. We see here and that x is a variable binding in f of x. Q is a metavariable that is not parametrized, but the fact as not being parametrized, when it goes inside the quantifier, any free variable that may appear there is not bound by the x. Okay. So in fact, in this system, we can write equations when on paper, typically you write psi conditions, okay, avoiding capturing free variable. The kind of reasoning we want to do here is as follows. So exist is defined in terms of negation and or. Now we have the De Morgan law that allows me to put the negation inside the for all. And now we have a law that allows me to distribute an or inside the for all. And okay, this is again by definition a for all of an implication. The kind of a thing I want to draw your attention here is the passage from, say, this formula to that one. Okay. Is obtained by an axiom. Okay. In fact, by instantiating an axiom, but this is done in a quite non-trivial way. And so that's why I want to mention next. Okay. We want to derive this thing here, that for all x not f of x or q implies for all x is equivalent to for all x not f of x or q. And now we have an axiom for the same formula, but not for a negated formula, but for arbitrary formula p. And what we need to do is to instantiate this axiom so as to produce the consequence we are interested in. Okay. And that is done by an operation of meta-substitution. It's such called because these P, Q, and F are formal metavariables in the system. In fact, they are metavariables parametrized by terms. And these are the ones that we need to substitute for. In this case, the parametrized metavariable P, which is parametrized by a parameter of type the individuals, has to be substituted by a negation of some other metavariable f of y. And so the idea is that there is this operation of substitution for metavariable that works a bit as follows. So I want to meta-substitute, so replace the metavariable P in the formula for all x, P of x. What I have to do is to first go inside the quantifier. So that's the first step. So you see that these definitions are compositional, and this will be an aspect of the theory that will be revealed. And at this point, I want to now meta-substitute P by by the assignment it is given. And that means to replace textually P by not f of y, which is what is in fact happening here. But at the same time, the parameters, kind of the actual parameters carried by the metavariable P have to be substituted by the parameters, the formal parameters of the substitution. Okay. So you see that this is a very intricate operation. Okay. It replaces metavariables at the same time using the common notion of substitution, in fact, capture avoidance substitutions for variables. Okay. And then this is done as you would expect. So to substitute x for y in not f of y is to do that inside the f of y, which is to go inside the parametrization of the metavariable and then do the actual substitution. Yeah. So what we are interested in here is in understanding actually and in fact programming these operations, both that of meta-substitution, which is the core of how you do equational deduction in this system, which in turn involves capture avoiding substitution, okay, which is already known to be quite a difficult thing to not only formalize but implement. I gave an example from logic. Now I want to give an example from algebra somehow, which is that of partial differentiation. So we have a type R of, imagine it's a ring. It has multiplicative and group structure, so additive group structure and multiplicative structure. And then this supports a notion of partial derivative. This is the partial derivative of a function that will be the R dot R. So in the formal system, this will be a binding operator instantiated at some point of R. Okay? And for that, we use this symbol delta, as usual. Okay? And one can axiomatize a theory. The one I'm using was recently put forward by Plotkin, where, okay, among other rules, there is this one that in fact is a generalization at the same time of the chain rule and the Leibniz rule. It says that to partial derivate the function that takes an x and give you f of g of x and h of x, you see f, g, and h here are again formal metavariables, parametrized f by two okay, yes, yes, by two terms, in this case g of x and h of x, each of which is parametrized by one possible term, in this case x and x. And the partial derivative of such composite function of two arguments at some point z is given by the addition of the multiplication of two partial derivatives, one that you take along the first direction and another one that you take along the second direction. Okay. The important thing here is not the exact nature of the law, which is what you expect, but how it gets translated in a formal system. Okay. So, in fact, where you can see there are many subtleties when you do this passage formulae. And what we want to do actually is to be able to, from such this syntactic description, deduce the formal syntax and then actually formally manipulate it with the equational deduction using this meta-substitution as was kind of indicated. So, for instance, if you look closely, something that you don't see in intuitive and in writing is that this partial derivative in this term is actually applied to terms that live in essentially different contexts. The first one is a closed term. Okay, x binds inside f and g and h, while the second parameter, the z, is an open variable. Okay, it's coming from the context in which you are describing this equation. And in fact, to make this formal, what you have to do is to take the operation for terms living in the same kind of context, while this is closed and this is open. And so to reason in very precise formal terms, in fact, within a proof of system, what you need to do is to give a translation where the term on the left-hand side is weakened to a context where z lives. And if you look down here, there is some delta zero, and this is exactly what this delta zero is doing. Okay. In fact, what the system that we have is takes a description as on top and formally translates it as one below, which is in fact a formal syntax within AGDA, and takes care that all the proper manipulation, including all sorts of weakening, sometimes contraction, are done formally, and also doing substitutions and avoiding capture and supporting even meta-substitution. Okay, so as one example, and this is something that is actually formal syntax within AGDA, again, is that from this generalization of both Leibniz rule and the chain rule, one can of course derive the unary chain rule. And to do that, we need to apply a meta-substitution for the former parameters here f, g, and h, which in the translation acquire names a, b, and c. And you see here is how it goes in the formal setting. We are going to use the axiom chain 2, and we're going to instantiate it with this meta-substitution here, where the first metavariable, which I was calling f before and got translated as a, which was taking two parameters, now takes one and forgets the second one. The second one is as before, and the third instance is instantiated with 0. And once we do that, we get a new instance, and this is automatically generated from the system, where then we see that we have a derivative of 0 that becomes 0, and then multiply by something remains 0, and we recover the chain rule. Okay, so this is a bit fast way to show you an example of how you do deduction in this system, but my point is to convey the idea, at least for the moment, that the system allows you this very precise formal reasoning, and it supports it by this notion of meta-substitution. Okay. Now, we have a paper with Dima where we explain a bit the system to some extent, how it's implemented, but we actually don't say where it comes from. And in fact, it comes from mathematics, and that's the real thing that I want to talk about in this talk. So really the purpose of the talk is to explain the mathematics that led to the development of this system. And so from that point of view, this work can be seen as quite sophisticated mathematical program construction. Before we go into that, I mean, I want to say one more thing about possible applications, about which I will be happy to hear any thoughts if you have. Just I have emphasized this idea of these systems to be used for formalization and reasoning, both in logic and programming. But I believe there is a place, they could play a role in symbolic computation. And this is both, again, in logic and programming, from the point of view of deduction system and calculi that you may wish to rapidly implement. In fact, in rapidly implement in a way that you have guaranteed correctness, but also perhaps in compilers where you're interested in abstract machines that may be formalized by these languages and not formal translations between them. Okay. So I just want to emphasize that it's not only about logic and programming, but we really want to, and the system has been designed to try to actually compute with these things. And in fact, this is shaped quite a lot of the theory. So now I leave the system aside, and I want to show the mathematical theory from which this came to. Okay, from the pure foundational mathematical point of view, this was quite well understood for a while. The beginnings of that are the pre-shift models of abstract syntax with variable binding that I developed with Plotkin and Turing. I'm going to give you a quick idea of what that is, because this is where the new model will come from. And in fact, I will use it to motivate the development of the new model. So in this setting, we have a set of types. These types have structure, but from now on, I will forget about that because this structure is algebraic and we know very well how to deal with that. Over these types, we consider a category of context and renamings. This is as you would do in programming language. If you are categorically minded, this is the free co-Cartesian category on the set of types. But think of context as list of types, and renamings have functions from the indices of the one list to the indices of another list, respecting the types. Okay? And from there, we built a universe of discourse, which is a pre-shift category. Is the set to the context parametrized by types. Yeah. The way to think about pre-shifts in this world is that they are terms. So say T of sub alpha at gamma it kind of can be thought of the terms of type alpha in context gamma. And this is really guides all the construction and intuition that comes later on, at least from the type theoretic point of view. A main example is the pre-shift of variable that is a representable. Is V at alpha and gamma is the mappings of alpha and gamma. That is the selecting all the variables of type alpha within context gamma. The important thing of this category is that they have certain combinatorial constructions that actually allow you to model systems, syntax. So sums, products, and more importantly, powers to representables. Perhaps some of you are familiar with this idea from cubical type theory, where you have, well, Cartesian one, at least you have this kind of same structure. And so some T beta, so this is to be thought of the types of the terms of type beta to the power B alpha, you can work out is nothing but the terms of type beta in the context extended by alpha. Okay. And now from this point of view, it's direct to kind of describe syntax in this new large universe of discourse. So as a basic example, consider the untyped lambda calculus. A term is a variable or an application or a lambda abstraction. And so this becomes in this world an isomorphism between some type T, the object of variables, pairs of T, and T to the representable. Okay. And in fact, we are not interested in any isomorphism, but in particular ones. And the particular ones are the ones that abstractly describe syntax, and they are the initial ones. So the development goes as follows. Given some syntactic signature, which is some kind of a description along these lines or along the lines that I gave in the code snippets, we generate a polynomial functor by the means of this combinatorial construction. And the abstract syntax, in fact, is constructed by the initial algebra. Okay. These initial algebras are the right notion because they give an abstract syntax in the sense of being independent of representation, purely characterized by the universal property. By initiality produce compositional semantics, and in fact also by initiality come with induction principles, which are the things we use to reason about syntax. In fact, there is a general thesis behind this idea that I use here, is that to me, type theoretic rules, they are nothing but syntactic description of polynomial diagrams. And the syntax that they generate is nothing but the initial algebra for the polynomial functor associated to the polynomial diagram. We will not go explore this in any further in this talk, but this is what I believe is happening actually in general, not just for this example. Okay, so this is the framework. We start with some syntax. It's a second order signature in the sense of having these binding operators. It generates a polynomial functor. This gives us a notion of semantics, which is the category of algebras for the functor. And by very well-known facts from category theory, we get a left adjoint that induces a term monad. And this term monad is describes, at least when the term monad as the empty presheaf describes the closed terms abstractly of the abstract syntax. Okay, the question is, how are we to produce computer implementations of this mathematical model? And there are two possibilities. You can do it in programming languages. The problem is that, in fact, I have done this long time ago when that work was developed. The problem is that, yes, what you are doing is ad hoc, and any implementation that you do has no correctness guarantees. So its better approach is then to do it in this very strong proof assistance, where you have strong invariants that hopefully will characterize correctness, and in fact they do, and where you can also compute at the same time. Okay, and but there is quite a bit of a problem. So when I started to work on this, I thought that this was kind of easy. You just get the mathematical model and you implement it in the machine. And as soon as you do that, and you actually want to enforce being able to compute, you run into problems. In fact, the first question that comes is that how are you going to implement this initial algebra? In category theories, typically its existence is argued by some kind of colimit construction of a very elementary form, but this is something that if you are to implement in the machine, needs quotients, and working with quotients sometimes does not allow you to compute. For instance, does not allow you to extract, even if, yes, when you're doing it constructively, witnesses for the equivalence classes in these quotients. Okay? So there are other places in the theory where quotients appear that you will see that makes things problematic. So the direction now is the other way around. Since the machine is not good enough to actually understand the abstract math, we're going to see if we can adapt the mathematics to the proof assistant. And what we need to resolve here is a big tension between the perceived models and what the machine actually deals very well with, which are families of index sets. Specifically, what we want to do is replace the category of context and renaming, FT, by the set of context, T star, which is nothing but the list on T, and see whether the mathematical theory that we know is the right framework on the left can be kind of mimicked in the right, or actually taken care of from the right. So here is the first, this is the direction to do this. From the mathematical point of view, it's a very trivial observation. Start with the category C. You want to talk about C, well, you want to talk about pre-shifts on C, but you want to do this from the point of view of index families. So consider the set of objects of C, namely C0. There is an inclusion of one into the other, and this generates adjoint modalities in the form of a monad and a comonad. This is by some very well-known canonical, I would say, Grothendieck theory. Okay, and this allows us to talk about pre-shifts in the context of families. Okay? And we can do it in actually two ways. One way is by using actions or diamond algebras, where diamond is the monad induced by this construction, or another way is by using coalgebras for this box, which is the comonad. In fact, it seems that the implementation has a preference for working with comonads, and maybe I can say something more precise about that later on, but both viewpoints are useful. Okay. So we freely add the algebra structure of C indexed by C0 with the diamond, or we co-freely add it with the box. Now, I know that in this community, you are very interested in modalities, and so there is a question that I put forward here that perhaps you are interested in. So, could it be possible that we can use these adjoint modalities in proof assistant to actually study pre-shifts from the point of view of index families? In particular, one possibility could be, can we design internal languages for pre-shifts that on which we work at the level of the proof assistant, but they have to be compiled down to the type theory, and we may do so just via these adjoint modalities. Okay, so that's a question that I have not explored. I will be interesting to know if you also find it of some relevance. What I'm going to show is that, at least for this example, this is quite important, because all the stuff that you can do in impossible that you can do with pre-shifts, now you can do it actually in a somewhat refined way from the point of view of index family, where these modalities, especially the box, play a crucial role. Okay. So now we are in families as universe of this course. So index sets, index over the list of types. We don't have a type of variables anymore, but we have a type of names. The names of type alpha and context gamma, there is only one, and this is only available when the context is unary, namely coincides with alpha. We have sums and product, but by forgetting all the perceived structure, we gain also some structure. Because T star, the list on T, is a monoid, so it uses a monoidal structure on the perceived category by day convolution. And so you see, by moving to this kind of less refined world, we get more type constructors that actually play an important role in developing the theory within the proof system. So there is actually a calculus that connects the perceived world with the index family world. And here are some sample equations. So for instance, variables are nothing but freely generated names. That's what this first equation says. And this gives me a notion of indices. In fact, as you would know from the Browne indices, if you have ever looked into implementations of syntax with binding. An index is the underlying index family of the variables, which is the underlying index family of the freely generated presheaf from the names. The operation of context extension that I talked about before, now it also appears in this word, but in the form of the deconvolution by means of a linear exponentiation. Okay, and then here are some other laws that are important. For instance, the free construction of F times free construction of G is free constructing over the tensor product, the day tensor product of F and G. And this calculus, in fact, is used within the implementation for certain purposes. So I'm going to indicate some now. So I should be finishing in 15 minutes, Carlo, is that right? Okay.
Yeah, we started a couple minutes late.
Okay, because I have too many slides actually, and maybe I'm only halfway now, but anyway, we'll see. Okay, so maybe I'll go a bit faster now. So what we're interested in here, as I said, is initial algebra semantics. And remember, for the lambda calculus, this was given an equation of this sort. And now I want to analyze it from the point of view of families. And if I do that, I see that a new equation appears, namely, at the level of families, we're working with indices instead of variables, and the exponentiation by representable becomes linear or deconvolution exponentiation by names. And this suggests that we should look at, in the setting of families, a new initial algebra, namely that of this highlighted construction. Okay. Now, why, I mean, this is a motivation for looking into that. Why is this going to work at all? Well, the idea is as follows. We're going to look at the signatures, look at the polynomial functors that they generate. They correspond by this kind of same process that I mentioned in the previous slide to polynomial functors in the family world. And the fact is that the initial algebras in the family world lift to initial algebras in the presheaf world. Okay. And why is this so? Because this is also a very basic category theory, and it's very general. If you have any comonad on some category E, and you look at the coalgebras, and any functor on E, endofunctor on E that lifts to the coalgebras allows you to lift initial F algebras to initial F lambda or lifted coalgebras. And this you do very straightforward by initiality, by building, using the distributive law that is implicit in this lifting. Okay? And so this is the mathematics behind the usual implementation, actually, of syntax as is known in practice and called intrinsically type encoding. And so what we have in the system is, if you give me a syntactic description of operators, possibly with binding, then we automatically generate by some script what is called an intrinsically type encoding, that uses exactly these index families in the way I was doing before, and matches precisely what is happening in the presheaf model. So this lifting theorem is very important because it says that if you solve an initial algebra on the bottom, namely at the level of index family, you can equip it automatically with coalgebra structure, which in this case means renaming or pre-shift structure. And we will see that coming in a bit. So that's all about syntax. What we want to do is talk about substitution for syntax. The substitution for syntax is a meta operation that given, say, terms in context gamma of type alpha, and for every type gamma in the context, some term in some other context delta of that type, will substitute this list of terms in the first one to produce a term of type alpha in context delta. And this has to be subject to action so that it is correct. In the pre-shift model, it amounts to monoid structure. Okay? And this involves something called the substitution tensor product that essentially encapsulates the definition of a term together with the substitution for it. Okay. Here and here. Okay. Now, this substitution tensor product, as you see here, is defined using a coen. This coen is a sum modulo quotient, and again, if we are to implement it directly in the machine, we have to deal with quotients, and this is problematic. So what we can do, well, before we go in this direction, we need to introduce the right notion of syntax that supports substitution. And so this is syntax with the following form. So we have some pre-shift T with the monoid structure. This axiomatizes substitution together with algebra structure, and the algebra structure and the monoid structure has to be compatible in a sense that is depicted in this diagram, that essentially says that substitution can be calculated structurally. So if I do a construction and a substitution, in fact, this is the same. I'm pushing my substitution inside the constructors, recursively substituting, and then taking the same constructor I was looking into. Yeah. So the first theorem we want to look at in this setting is that we have this notion of a sigma monoid, which is that of syntax with substitution. There is a forgetful functor. This has a left adjoint, and the left adjoint can be described itself as an initial algebra. Okay. And this provides us with a free syntax with substitution. Okay. The initial algebra, the formula is given there. The important thing about this formula is as follows. First of all, it explains, or actually gives, a notion of syntax with metavariables and with parameters. So something in this free syntax with substitution can be thought of as a term with variables, or metavariables parameterized by some terms, or constructors, possibly with binding nullities. And the other thing is that it aligns with practice, okay? In the sense that here from syntax, we generate automatically the notion of the associated notion of substitution, in fact, by induction, and therefore guaranteed to terminate, and moreover, with the probably correct, namely satisfying the properties that you expect. Okay, so now we want to do this in the family setting, and we see that there are problems. So the first is that this substitution tensor product has to be defined for families where the coend is replaced by a sum, and this traction is not a tensor product anymore, but it's a skew monoidal, as was used by Bordel, Hirschowitz, and Lafont quite recently. And this actually complicates a bit the theory. Interesting thing is that monoids for this Q monoidal structure actually correspond one-to-one with abstract clone, and so anyway we know that monoids for this structure is the right notion of substitution. So nevertheless, we can talk about substitution, syntactic substitution in the context of family. Rather than doing it with this tensor product, the implementation leads you to consider the closed structure associated to this tensor product, which is also skew, of course. Okay. And this is the kind of structure you have to look at. You have to look at families F with the point for variables, a substitution now, which is given in carried form, and then constructors. And these constructors are again, substitution for this construction is again compositional, now expressed in the closed form. So if I do a construction and substitute, this is the same as doing the substitution, pushing through the term and then taking the constructor. Now, we prove a similar theorem, and in fact, this is formalized in the context of families. Okay. For every family X, we can consider the initial algebra for a structure that has variables, these metavariables, constructor and the constructors of the syntax, and this is a free sigma mono. With this result, what we can do is actually show the correctness of automatically generated these intrinsically typed encodings as before, but now enriched with metavariables. And the difference with what I was showing before is that we have a new clause that we are constructed terms parametrized by a family that provides you with the metavariables you want to build your syntax with, and a constructor that given a metavariable, and a substitution for it produces a new term. Okay, so let me see. So let me just, the ingredients of the proof, let me just gloss over them. Maybe if there are questions, I can talk about that. So that I can move on to the other structure that we are interested in, which is this operation of meta-substitution, this substitution for metavariables. Okay. What happens in the pre-shift model is that this free sigma monoid, some syntax with substitution monad, happens to be enriched. And because it's enriched, you get a right notion of meta-substitution operation, which is nothing but the internalization of the Kleisli structure of the monad. Okay? In this form, you can read it as if you have a term M built from metavariables taken from some set of metavariable X. And now you have an assignment for each of these metavariables of some terms now taken in a context with metavariable Y, then you produce a new term with the context with the metavariables taken from Y. And what we want to do now is to export this, to understand this actually from the point of view of families. Which is not quite simple. I mean, it was proving this enrichment was not simple either. So, okay, so the internalization of this operation in the context of family, in fact, we do it linearly, namely that it involves the deconvolution. So you read this that if you give me a term with metavariables in X, and now you give me a mapping for these metavariables to terms in metavariables in Y, then I will produce a term with metavariables in Y. Okay. In elementary terms, and that's the reason for which one needs to use these linear operations, we have the following expression. Give me a term with metavariables in X in some context gamma 1. Now, for whatever context or parameters delta, give me some mapping from the metavariables as specified by X in this with these parameters delta into a context of terms using metavariables in Y in some context gamma 2 extending with the parameters. Then I will produce a term with metavariables in Y in the context that uses both gamma 1 and gamma 2. Okay. And this is the kind of most general notion of meta-substitution that you can use, and in fact that you need for doing equational reasoning. Okay, so this is how you induce the meta-substitution by categorical means, but let me just gloss over that and explain what's really happening at some kind of intuitive level. It says that suppose you want to meta-substitute some meta-variable m parametrized by the bunch of type terms t as given by a meta-variable mapping sigma. The result of doing this is to do a substitution, which is provided to you by the sigma monoid structure, on what? On substitution that recursively meta-substitute in all the terms of that appear as parameters t using the same substitution sigma in an extended context, and that is the WK is a weakening of this term. So that's kind of the idea of this very sophisticated operation. And with this, in fact, we have actually implemented in Agda. And what you can do now is get a formal system that actually is equational deduction for second-order logic, or second-order equational logic. Okay? So in this system, we parameterize it well by the syntax, whatever syntax you decide to work with, a bunch of axioms given by this parameter here. And once these are given, essentially the formalization is as you would write on paper. Okay, so every axiom, so you have a deduction rule that says every axiom is the derivable. That's this part. Oops. If two terms are equal, then they are derivable as an equation in the system. Symmetry, if t equal less than s equal t. Transitivity, as you expect. And then there is only one deduction rule of interest, let's say, and it's this one here. And this is essentially saying that if, yeah, so let me see. If t equals s, as you see there, and you have two substitutions, psi and psi, then you can meta-substitute both in t and s to derive an equality there, provided again that, yes, point-wise, these two meta-substitutions are equal. So my time is running out. So yes, let me just quickly conclude. So the problem I look at in this talk was to automatically generate in a generic form second-order abstract syntax with notions of substitution and meta-substitution to manipulate it that are probably correct. I have not said much, but this also provides us with algebraic models that give you compositional interpretations. And this is in fact how both substitution and meta-substitution operations are derived. And this led to some Agda implementation that allows us to do deduction and also computation of these things, including pretty-printing of these terms for arbitrary generic second-order theories. The most interesting thing from the point of view of implementation, I would say that is mathematically inspired, And in fact, it's a kind of sophisticated exercise in correct program construction. There are many directions for further work, but my time is over, so thank you very much.
Okay, thank you, Marcelo. So let's all silently applaud the speaker. Okay, then if anyone has a question, just go ahead, unmute yourself and ask. Okay, I guess let me start. So can you go back to the AGDA code you were showing at the very end? Just to...
Yes.
Yeah, exactly. So I mean, the second rule, I guess, is essentially saying that the equality of the theory is reflexive, right?
Yes, this is a reflexivity. Yes.
Is there any reason to write it this way instead of that way?
So,
because I guess if you wrote down reflexivity, then this would follow, correct? Or
yes, it's the same essentially. Yes.
Okay, yeah, just curious.
I have a question. So first of all, you said that you didn't want to use quotients in the implementation, right? They weren't computationally well behaved.
Yes.
So is that still true with you know, now that we have like cubical AGDA, for instance, there's still issues for you? Well,
I don't know what will happen with cubical AGDA.
Okay.
But one thing is that once you have quotients, yes, you are inside. You are inside your terms, or for instance, if you consider a term construction that is not like this intrinsically type encodings, but as colimits, which are quotients of sums, then your terms are equating modulo these quotients. And the point is that if I ever want to, or one point at least, if I ever want to print a term, I need to actually put it in some canonical form.
Yeah.
You see?
Okay, so it's not just that quotients are poorly implemented in the type theory, it's that you'd want to avoid quotients altogether.
No, it's yes, I think that's the main point, is that once you have quotients, yes, they become equivalence classes, and then you need to implement something that will be able to extract, well, if you want to actually print these terms, you need to implement something that will extract a canonical representative out of the equivalence class.
Right.
So let me just say something else about this. Long before this work, also we'll try to do in Coq with another student, Nathaniel Arco, some kind of implementation, in fact, using the colimit construction. And even in the most simple examples, it would take a very long time to actually do any computation, to produce any output. You see, so from that practical point of view, also was not feasible, that approach.
Oh, and then I had another question, which is this library in AGDA ready to use for other people? Is it released?
Yes, there is a link in you look at the abstract of the talk, there is a link, and you go there, and there are all these examples are in there. Not exactly the same, because here I massage them so that some syntax will look a bit nicer, so that it could be easier to absorb as because I'm going that fast. But yes, all these codes are taken from there.
Great, thank you.
And I pasted that link in the chat also.
Maybe one quick question related to Max's question. Sorry, my camera's busted. But so I was wondering whether you could prove that the inductive type that you want to use for syntax satisfies the universal property of the colimit. I mean, without using the usual construction as a quotient.
So
just directly proving the universal property.
That could be possible. It should be true, of course, in the mathematical sense. Whether one can do it in Nagda, one would have to try, but it should be possible. Though one thing I want to emphasize is that is using that this is a colimit is completely unnecessary. In fact, all the development just uses the universal property of being an initial algebra. And this is enough for everything. And this is in fact what what this inductive type is. The eliminator of the inductive type actually gives you straight away that in fact is an initial algebra in the categorical sense. And from there, all the theory develops. You don't need to know that this is a colimit or anything. It's completely immaterial.
Thank you.
Quick follow-up question on that. So do you, I'd imagine that somewhere you'd need function extensionality to prove.
Oh, yes, in a lot of places.
So you're postulating that, are you? Presumably?
Yes, we're postulating that.
And just another quick question. Do you and Dima, are you just sort of, as it were, using vanilla Agda, or do you use its meta-programming facilities?
Well, the development in the machine is Dimas. I know he used rewriting, but I don't think it's for convenience more than anything. So yes, I don't think that is a big deal. And of course, okay, there are many things I skip and I went or I went very fast. For instance, when you induce the substitution, to be able to prove that it satisfies the law is actually non-trivial. It's easier in the pre-shift model because everything is correct. You have a real strength, you have a real structure. In the index family model, this real structure gets skewed. And so there are problems. And so you need to start considering properties of this map, in particular equational properties of how this map behaves with respect to renaming. And this involves certain equations, which are invariance under some kind of renaming or naturality or things like that. But typically all the proofs for this equation are just reflexivity proofs. They're really trivial. There are no really interesting proofs of the sort. So it's
I have a question. So here the category of context, it's fixed in some way. It's list or it's list of types. What would it take to have it as parameter, like to ask for any context-like category and types? Because like this is for, with this, I'm convinced that we can do any kind of simply type-ish lambda calculus. But for example, for system F or other things, it would have to be a more complicated category of context.
yes. So yes, there are some questions actually. So this is an interesting point. So here I said list. We used list, but in fact, really the development is based on the structure of the category of context, which is the free co-Cartesian category. So now, whether you can take an arbitrary co-Cartesian category, I think it's true. In fact, the whole thing should be parametrized. We have not done it yet, but it should be parametrized on a category of context with universal property structure. And in this way, you could provide different implementations by certain kind of De Broglie indices or De Broglie levels, or that's one direction. Now, if you want to move to more sophisticated type theories, which are the directions that I have in the slide here, so already it's non-trivial to R linearity, though I know how the mathematical theory should be developed for that in all these directions that I mentioned. For polymorphism and system F, I also know the mathematical theory, and it has to be done in two steps. The first step of which is this one that we have done here. So if you look at you see in the system F, the type structure again gets shifted, and now we have types with variable binding. So we would use that theory, the theory we have here of types with variable binding, to generate syntax for them, and then what you have to do, which is something we did in the mathematics in a paper with Makoto Amana, to build categories of context on top of this syntax that you have already generated that now we have in the computer. And so there is an extra layer to add on top of this work. It's not done. I believe it's going to happen, but it takes a bit of time.
And just a quick follow-up, like, do you have any hope that we can, if we loop the thing, can we perhaps have a dependent type theory formalizing with this kind of structures? I mean,
so I'm afraid I didn't get the question, kind of cut, or if we do.
If we loop around, can we have dependent type theory modelized?
Oh, dependent types. Yeah, okay. That is so. I have in my not in my head how this should be, the version of this for dependent type theory. Whether what one needs to put it in the machine, for certain, I will only know once we start doing it, and it's in the directions to do it.
Okay, maybe one more, not particularly about this talk, but something that mystifies me about the whole approach is that somehow variables are very much like nullary metavariables. Would you agree with that? And
yeah, in fact, I not only agree. So you look at the paper on equational second-order equational logic, it's a fact. They're yes. So if you have a variable, it's equivalent to having a unary. From the point of view of deduction, it's equivalent to having a nullary metavariable. In fact, I would say that what we call variables in universal algebra, they are actually unary metavariables.
But so the question is, isn't the whole framework kind of redundant in that sense? Would you know how to eliminate this redundancy?
No, I don't understand what you mean by redundancy. I don't understand. I want to, maybe I want to talk about open terms with no metavariables, and that's the role of having variables in the system, which I wouldn't be able to do otherwise. So I don't see any problem.
Well, it would be like closed terms with only nullary metavariables.
Yes, but maybe I don't want to. Yes, so it does more ad hoc than what I'm proposing, which is no metavariable whatsoever and allowing variables. So I don't. Yeah, I don't see. Maybe it's a matter of taste. I don't see the problem.
Okay.
But certainly, from the technical point of view, they are interderivable by this meta. Yes, you can take a variable. Yes, in fact, that's another way to put it. This meta-substitution is so powerful that it allows you to mimic substitution, capture avoiding substitution, because capture avoiding substitution is built inside the meta-substitution.
Any other questions? Okay. Well, is there anything you would like to say about this, the future directions, since we have a few minutes?
Well, I can say, so one thing that we're already doing with the master student is that to use this to actually get formalization of some system by Nanevsky, Senin, and Pientka, which is called simply type contextual modal type theory. So in there, you extend simple types with new type constructors. These are contextual model types, and that are used to give types to these parametrized metavariables. And this is kind of it's a little extension, and so we are exploring that. On the things to do, we talk about polymorphism and type dependency. Type dependency is, of course, the more difficult one. One question is how you add the linearity here. And I think it's of interest in several directions. So for one thing, in programming language, at least people are interested in dual, linear, and Cartesian calculi. So that's one thing. But also, this syntax does not incorporate things that you have in type system, also in programming languages, patterns, as you use, for instance, when you program with abstract data types. And so, I know in the mathematics how you actually have syntax, not only with variable binding, but with pattern binding operators. As you know from programming language, this pattern need to be linear, and so first one needs to incorporate linearity to be able to put these patterns, but that should also happen along the way. And maybe one final little comment perhaps is that these things that I said are automatically generated at the moment, they're automatically generated by a Python script. So the Python script inputs this some text specification and spits some Agda code. This Agda code has these inductive families that formalize the syntax with automatically generated initiality proof that then gets into inside the whole framework and allows you to derive everything correct and automatically. One question that passes me is whether this kind of thing can be done within a proof of system itself by some kind of reflection. And when I say reflection, I don't mean the one that is already in Agda. The question I would see it in a more broader perspective is which kind of system we need to be able to do this programming with reflection within the system itself. Okay. So I don't know. I think that's an interesting thing to explore. I don't know the answer. But certainly it's a reflection that does not use strings to encode, but uses these more abstract types to encode. for abstract representative families. Yes, maybe I'll just can leave it there.
Okay. Well, maybe let's just thank our speaker again. And I'll stop